The particle model of matter is widely used to predict the behavior of solids, liquids, and gases. This has a range of applications in everyday life, like engineers designing vessels to withstand high pressures and temperatures, such as submarines and spacecraft. It also explains why you can't make a good cup of tea high up a mountain. The particle model of matter states that all matter around us is made up of tiny chunks of mass called particles. Depending on how these particles are arranged, the object they form can behave very differently. These different arrangements are called the states of matter. Almost all of the matter we see around us is one of just three kinds: solid, liquid, or gas. In solids, the particles are held closely together by very strong bonds that force them to remain in a given pattern. These particles are not able to move anywhere else, but they are able to vibrate around their fixed position. In liquids, the bonds between the particles are weaker, which means the particles are able to move over one another and flow. They are still unable to escape completely, but it is this property that allows a liquid to change shape depending on the container it is put in. Finally is a gas. The particles in a gas have no bonds at all between them, which means they can move completely freely. Like a liquid, gases can change their shape to fill a container, but unlike liquids and solids, they can also change their volume. If we look at the particles in different states of matter of a material, we can see that in a solid there are many more particles crammed into an area compared with a liquid or a gas. Another way of saying this is that solids have more mass per unit volume than liquids or gases. This is called density. The more mass found in a certain area, the greater the density of that object. We can calculate the density of an object by finding its mass and dividing that by its volume. For this equation, mass is measured in kilograms, volume in meters cubed, and density in kilograms per meters cubed. But be careful, if you change the units of either mass or volume, then the units for density will change too. The main challenge with finding the density of an object is working out its volume. If the object is a regular shape, like a cube or cylinder, it is relatively easy. You just use the formula for finding the volume of that shape. For example, a cube would be width times length times height. If the object is not a regular shape, like a chess piece for example, then you must use an experimental method to find its volume. First, you fill a container to the brim with water, then carefully lower the object into the water, catching any water that spills over in a second container. The volume of the water that spills over will be the same as the volume of the object that you are testing. Simply measure the volume of the water with a measuring cylinder. In both cases, once you have measured the mass using a balance and found the volume, you divide the mass by the volume to find the density. Materials are not stuck as being one state forever. Under certain conditions, they are able to change between the three states of matter. This is called a state change. Depending on which state of matter the material is coming from and going to, it has a different name. Solid to liquid is melting, liquid to gas is boiling, gas to liquid is condensing, and liquid to solid is freezing. Finally, in specific conditions, some materials are able to undergo sublimation, which is changing from a solid directly into a gas. An example of this is carbon dioxide or dry ice. These changes can be seen on a graph. This graph shows how the temperature of an ice cube changes over time as it is heated. Initially, the ice cube's temperature increases until it gets to 0 degrees Celsius. At this point, the temperature stops increasing as all of the energy being given to the ice cube is going into breaking bonds. Eventually, the ice cube melts into water and the temperature continues to increase. At 100 degrees, the same thing happens, only this time the water is boiling to make steam. All of these state changes are called physical changes. This is because if you reverse the change, then the material will recover its original properties. For example, if you heat an ice cube, you get water. Then if you cool that water, you get an ice cube back. For a chemical change, this is generally not the case. Particles in a material can have energy in two different stores: in their kinetic store due to the movement of the particles, and also in their potential store due to their state. If we add together these two stores of energy, we find the total internal energy of the system. We can change this internal energy in two different ways. The first way is by changing the temperature of the system. To do this, we supply it with energy, usually heat energy. Depending on the material we are trying to change the temperature of, this can require different amounts of energy. For example, 1 kilogram of aluminium needs 920 joules of energy to increase its temperature by 1 degree. whereas 1 kilogram of water needs 4,200 joules to achieve the same thing. This is called the specific heat capacity of the material, the energy required to increase the temperature of 1 kilogram of material by 1 degree Celsius. We can calculate the energy required for a given temperature change using the equation energy equals mass times specific heat capacity times temperature change. We can see from the equation that the amount of energy we need depends on the mass of the material, and the more material needs more energy, the material we are dealing with, and the temperature change we want to achieve, with a greater temperature change requiring more energy. There is another way we can increase the internal energy of a system, and that is to change its state. The further up the states we go, the more internal energy the system will have. Just like before, we need energy to make these changes happen, a lot of energy. The energy required to boil 1 kilogram of water is 3,360,000 joules. That's enough energy to heat the same water up by 800 degrees. This energy requirement per kilogram is called the specific latent heat of the material. Every material has two of these specific latent heats, one for solid to liquid called fusion, and one for liquid to gas called vaporization. These also work for finding the energy lost by moving backwards down the states. We can calculate the energy needed to change the state of a material using energy equals mass times specific latent heat. We must be sure to pick the correct specific latent heat for the state change that is occurring. Taking a closer look at a gas, the particles are in constant random motion. That means moving in random directions at random speeds. That doesn't mean we can't tell anything about this motion though. If we were to measure the average speed of the particles, we would find that it's related to the temperature of the gas. As the temperature of the gas increases, so does the average speed of the particles. This is because increasing the temperature of the gas supplies the particles with a little more kinetic energy, and more kinetic energy means they're going to be moving faster. This change in speed can have an important impact on the container as well. When a gas is held inside a container, the particles are constantly bouncing off the walls. When they do this, they exert a small force on each side of the container. As there are huge numbers of particles doing this every second, this force adds up to cause pressure on the walls of the container. If the particles are moving faster, that means there are going to be more collisions with the sides of the container, and therefore more pressure. The temperature of the particles and the pressure exerted are proportional. Pressure and temperature aren't the only parts of this equation, however. We need to factor in the volume of the container. If we increase the container's volume, then the gas particles will have to travel further through each collision, therefore reducing the number of collisions per second, and the pressure decreases. The volume of the container and the pressure are inversely proportional. We can calculate the changes to pressure and volume using the equation pressure times volume equals constant. That means that the constant value must remain the same when any change is made, so doubling the pressure must cause the volume to halve. This relationship only works if the gas is held at the same temperature, however. Take the example of a bicycle pump. The way it works is a person pushes down on the piston of the pump, which compresses the air in the cylinder, forcing it down the hose and into the tyre. The reason the air moves down the hose is that reducing the volume of the cylinder causes the pressure inside it to increase. The air then flows from high pressure to low pressure in the tyre. There is also an unwanted heating effect during the pumping process. If you try this yourself and touch the side of the cylinder, you will find it is hot. This is due to the fact that when you push down on the pump, you are transferring energy, or doing work, on the gas inside the cylinder. Doing work on a gas increases its internal energy, which can cause a temperature increase.